Hi guys, so I hope you enjoyed exercise 7 and let's look at the possible answers. So question 1 said for each of the following compounds predict the type of chemical bond taking place and use Lewis diagrams to show the bonding mechanism. So the first one we have is lithium chloride. So if we calculate the difference in electronegativity, chlorine has a electronegativity of 3.0 whilst lithium has an electronegativity of 1.0. So in total, it gives an electronegativity difference of 2.0. This is greater than 1.7, and we know it's a metal and a non-metal, and therefore we will say it is an ionic bond. So if we use Lewis diagrams, lithium has got one valence electron, chlorine has got 7 valence electrons. So lithium will transfer its one electron to chlorine so that they produce a lithium ion and a chloride ion. And these will then now bond in a crystal lattice or ionic lattice structure where we've got a ratio of one lithium ion for every chloride ion present in this ionic lattice. Our next example is beryllium fluoride. Now, our electronegativity difference here, fluorine has an electronegativity of 4.0 and beryllium has an electronegativity of 1.5, which gives a difference of 2.5. Once again, it's a metal and a non-metal, so we say it is an ionic bond. Now, beryllium is in group 2, which means it has 2 valence electrons. So when it reacts with fluorine, we will need more than one fluorine atom. We actually need 2 of them. So that's my first one. Now you can either write a 2 in front here, or you could just repeat the ion below. And you can just indicate, and this is why it's sometimes better to have the 2 ions that you, or the 2 atoms that you're indicating, because it's easier than to indicate the transfer of the electrons. So one of them going there and the other going there. So what it produces is beryllium 2 plus we will have 2 fluoride ions. And these ions will bond in an ionic lattice to form our beryllium fluoride. So this, once again, you can either repeat it like I'm doing here. So this is one option for representing this ionic bond formation. The other option would be to put a 2 in front there to indicate that it's repeated. So that would be your other option. Okay, if we then move on to the next question. In the next question, we've got calcium bromide. So the electronegativity between difference between calcium and bromine. Bromine has an electronegativity of 2.8, whilst calcium has an electronegativity of 1.0. This gives a value of 1.8. It will still be an ionic bond. Why? Because we've got a metal and a non-metal atom bonded. So to indicate the bond formation, calcium in group 2 has 2 valence electrons. We will need 2 bromine ions, seeing that it needs to transfer electrons to 2 of them because each bromine can only accept 1 electron. So that would be our transfer, and that will lead to the formation of a calcium ion and 2 bromide ions, which then will finally be attracted and bonded in an ionic lattice where you've got calcium 2 plus and then 2 of your bromide ions. Our next example is potassium sulfide. So the electronegativity difference now 2.5 minus 0.8, which gives a difference of 1.7. But guys, it's still a metal and a non-metal. So therefore it is ionic. Okay, so remember those rules are just a rule of fun. It's not set in stone. It's not a law. So in this case, potassium is in group 1, so it only has one valence electron, whilst sulfur is in group 16. So it can accept two valence electrons. So we will need two potassium atoms so that it can donate its electrons, transfer its electrons to there and there, which will lead to the formation of two potassium ions and one sulfide ion with a charge of 2 minus. So our final step then would be where they bond in the crystal lattice. We will have two potassium atoms bonded to our single sulfide ion. Question 1.5 asks for the electronegativity difference between aluminium and oxygen. If you calculate that electronegativity difference, it's 3.5 minus 1.5, which gives a difference of 2.0, and it will be an ionic bond. In this case, once again, a metal and a non-metal. Just for interest's sake, I want you to go and see what they've classified aluminium as at the beginning of this year, end of last year. So just go and look. So we will need, in this case, aluminium has 3 valence electrons, and oxygen can accept 2 valence electrons per atom. Now, aluminium oxide will have the formula Al2O3. So we need 2 aluminium atoms and 3 oxygen atoms. So to better indicate it, I think it's better to actually repeat these structures to indicate the transfer than writing out these numbers in front and then you can't see how these electrons will be transferred. So if I have 3 aluminium atoms here and I've got I just need 2 of them, not 3 of them. 2 of them and 3 oxygen atoms. So there's my 3 oxygen atoms. So the first one will transfer there and there, and that one will be there and there. Let's just take it from there, and then this one will be from there and from there. So that would be how it's transferred, and it will produce 2 aluminium ions, 3 plus 2 of our oxide ions. And our oxide ions, not 2, 3. 3 oxide ions, each with a charge of 2 minus. Okay, and your final step then will be where these bond in a crystal lattice. And it's when it gets to this where it actually becomes easier to just write the numbers in front to indicate how they are repeated, because this is kind of tedious to draw out 3 times. So my suggestion would be it's easier to write it like this. That is your crystal lattice and the ratio that these ions bond in. Okay, final question. Question 2 says explain why magnesium oxide has a greater melting point than sodium chloride. Okay, so like I explained earlier, the charges of the ions Mg2 plus O2 minus, let's just make sure you know that's a minus, that it doesn't look like a plus. O2 minus versus Na plus and Cl minus is greater in magnesium oxide, leading to a greater electrostatic force of attraction. So this would lead to a greater electrostatic force of attraction. So this means it's stronger ionic bonds. Okay, hope you enjoyed this lesson, guys. Cheers.